A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
You know, Corn, this whole show runs on GPU compute, and we wouldn't be here without Modal.
Seriously. And that's what powers all our text-to-speech. Everything you're hearing right now.
They're an AI infrastructure platform. Developers use them to run GPU workloads in the cloud with zero infrastructure headaches.
If you're building anything with AI, check them out. Modal.com. Here's what Daniel sent us this week. He's asking about what happens to RAG when it lives inside an AI agent rather than a simple chatbot. And his argument is that the differences are more substantive than most people realize. In a chatbot, RAG is pretty mechanical. User asks a question, relevant chunks get retrieved, stuffed into context, answer comes out. But inside an agent, it becomes a multi-step, decision-driven process. He wants us to cover the key architectural differences: tool-augmented retrieval, iterative search, routing decisions, write-back capabilities, planning-aware retrieval, and dig into how frameworks like LangChain, LlamaIndex, and Pinecone are handling this. Good one, Daniel.
Herman Poppleberry here, and yes, this is a topic I have strong feelings about, because the framing of RAG but in an agent undersells how different it actually is. It's not an incremental upgrade. The mental model you need is completely different.
Let's start with the baseline, because I think the chatbot version of RAG is so well understood at this point that it's almost boring to describe. But the boring part is important context.
Standard chatbot RAG is a deterministic, one-directional pipeline. User sends a message. That message gets embedded. You pull the top K most similar chunks from a vector database. Those chunks go into the context window, and the LLM generates a response. Byte goes March 2026 technical breakdown put it cleanly. Standard RAG is a pipeline where information flows in one direction from query to retrieval to response, with no checkpoint and no second chance. That's the whole thing. And it works really well for direct, unambiguous questions against a clean knowledge base.
The classic, what's our return policy? Use case.
Right, but it has 3 failure modes that all share the same root cause. Ambiguous queries, the system takes the user's message as is, retrieves whatever scores highest on similarity, and hopes it's relevant. Scattered evidence, if the answer lives across multiple documents, Standard RAG has no concept of checking a second source when the first comes up short. And false confidence, retrieval returns something that looks relevant based on similarity scores but doesn't actually answer the question, and the system cannot tell the difference between looks relevant and is actually correct.
And all 3 of those failures come from the same place, which is that the system never looked back at what it retrieved.
There's no reflection step. The pipeline runs and the result goes out. Which brings us to the core architectural shift. Chatbot RAG is a pipeline. Agentic RAG is a loop with decision points. NVIDIA's technical blog frames it as the difference between simple, query, retrieve, generate, and dynamic, agent queries, refines, uses RAG as a tool, manages context over time. Those decision points are the entire value add.
So let's go through the 5 differences Daniel flagged, because I think they build on each other. The first one, tool-augmented retrieval, is actually the most fundamental, isn't it?
It's the foundation everything else rests on. In a chatbot, retrieval is mandatory. Every single turn automatically, no matter what. In an agent, retrieval is a tool, one of many tools the agent can choose to invoke or not invoke. The agent decides whether this query even needs external retrieval, what query string to actually construct rather than just passing the raw user message, and whether the results that came back are sufficient or need refinement. The Qdrant article on agentic RAG describes the simplest version of this as a routing agent. A simple router that chooses a path to follow is often described as the simplest form of an agent. Such a system has multiple paths with conditions describing when to take a certain path. In the context of agentic RAG, the agent can decide to query a vector database if the context is not enough to answer, or skip the query if it's enough, or when the question refers to common knowledge.
The skip the query part is underrated, because if the agent already knows the answer from training data or from context earlier in the same conversation, firing a retrieval call is just wasted latency and cost.
And this alone changes the economics of the system dramatically. Standard RAG latency is 1 to 2 seconds per query. If you're making retrieval conditional rather than mandatory, you're avoiding that cost on every turn where it's not needed. But here's where it gets more interesting. The agent doesn't just decide whether to retrieve, it decides how to construct the query, not the raw user message verbatim. A rewritten, more targeted query based on what the agent actually needs to know at that point in its plan.
Which leads directly into the second difference, multi-step retrieval. Because if the agent constructs a query, gets results back, and then decides those results aren't sufficient, it can go again.
This is the React framework, reasoning and acting. The agent alternates between reasoning about what it knows and taking actions to learn more, running multiple retrieval steps with evaluation between each one. 3 things unlock from this. Query refinement. Before searching, the agent rewrites an ambiguous query into something more specific. After searching, if the results look weak, it reformulates and tries again. Self-evaluation. After getting results back, the agent examines them. Is this relevant? Is it complete? Does it conflict with other information I have? If the answers aren't satisfactory, retry with a different query, a different source, or both. And the Archive survey on agentic RAG, which came out of Cleveland State and Northeastern in early 2025, identifies a third pattern they call corrective RAG, a distinct architecture where a relevance evaluation agent assesses retrieved documents, a query refinement agent rewrites queries, and a separate external knowledge retrieval agent performs web searches when internal context is insufficient.
5 distinct agent types in that architecture, right? Context retrieval, relevance evaluation, query refinement, external knowledge retrieval, response synthesis.
5 agents, each with a specialized role. But here's the thing I want to flag because it's genuinely underappreciated. The self-evaluation step that makes all of this powerful is also the deepest problem. You're using an LLM to judge whether the LLM's retrieval was good enough. ByteByteGo called this the evaluator paradox. Asking the same LLM that might hallucinate to judge retrieval quality is a fundamental circular dependency. The system's ability to self-correct is only as good as the LLM's ability to assess relevance, and that ability is imperfect in exactly the situations where you most need it to work.
So the agent is most likely to fail its self-evaluation precisely when the query is most ambiguous or the retrieval is most unreliable. The times when you'd most want a second opinion are the times you're least equipped to give one.
The practical workarounds are to use a different, smaller model as the evaluator rather than the same model doing the generation, or to use deterministic signals. Document recency, source authority, citation count, rather than LLM judgment for the evaluation step. Neither is perfect, but they reduce the circularity.
Okay, third difference, routing. And this is where the architecture starts looking genuinely different from anything a chatbot does.
In a chatbot, there's typically one knowledge source, the vector database. In an agent, there can be many, and the agent must decide which to query. The Archive survey's taxonomy of a single agent router describes the decision tree, structured databases for queries requiring tabular data, handled via text to SQL against PostgreSQL or MySQL, semantic search for unstructured information, web search for real-time or broad contextual information, recommendation systems for personalized queries. IBM's documentation identifies routing agents as a distinct agent type. Routing agents determine which external knowledge sources and tools are used to address a user query. They process user prompts and identify the RAG pipeline most likely to result in optimal response generation.
And Qdrant adds a nuance here that I think practitioners actually run into. It's not just which database, it's which retrieval strategy within a database. Dense vectors versus sparse vectors, depending on whether the user is doing semantic search or keyword lookup.
That's a real engineering decision that gets exposed once you have an agent layer. If your users are searching with specific keywords, sparse vectors are more efficient. For semantic queries, dense vectors. The agent needs tooling to decide which to use dynamically, and that decision isn't always obvious from the query alone. Now, the multi-agent version of routing takes this further. The Archive survey's multi-agent agentic RAG architecture distributes retrieval across specialized agents, one handling SQL-based structured queries, one handling semantic search for unstructured data, one handling real-time web search, one handling recommendation systems, and critically, these run in parallel, with a coordinator agent synthesizing results. That's a fundamentally different architecture from any chatbot RAG system, not just an incremental improvement.
Let's talk about the fourth difference because I think it's the one most developers genuinely haven't thought through right back. The knowledge base updating itself.
This is the most underappreciated difference in the entire list. In a chatbot, the knowledge base is static, read only during inference. You build it once, you query it forever. In an agent, the knowledge base can be a living, writable system. NVIDIA's technical blog explicitly identifies this as a core capability, supporting feedback loops where the AI agent's actions or insights can update the knowledge base, creating a cycle of continuous improvement. Practical patterns. An agent researching a topic discovers a new fact not in its knowledge base and upserts it as a new vector record for future retrieval. A customer support agent resolves a novel issue and writes the resolution to the knowledge base so future agents can retrieve it. A research agent synthesizes findings from multiple sources and stores the synthesis as a new document, enabling future agents to retrieve the summary rather than resynthesizing from scratch.
That last one is interesting because it means the agent is not just consuming knowledge, it's producing it. The knowledge base gets richer with every agent interaction,
which transforms the vector database from a static artifact into a dynamic, evolving knowledge graph. This is what NVIDIA means by AI agents that get smarter. But here's the governance challenge. LangChain's 2024 State of AI Agents survey, over 1,300 professionals, found that most teams allow either read-only tool permissions or require human approval for more significant actions like writing or deleting. Very few allow their agent to read, write, and delete freely. Larger enterprises with 2,000 plus employees lean heavily on read-only. Smaller companies are more willing to experiment. The tension between safety and capability here is one of the defining governance challenges right now.
It makes sense to be cautious. An agent that writes back incorrectly is an agent that poisons its own future retrieval. One bad upsert and every subsequent query that hits that document gets contaminated.
And unlike a bug in application code, a bad write to a vector database is invisible. It just looks like a slightly off response with no obvious error trace. Debugging is hard enough in agentic systems without adding corrupted knowledge bases to the mix. The byte-byte-go analysis puts typical agentic debugging as substantially more difficult than standard RAG precisely because the execution path is variable. You can't just replay the same query and expect the same retrieval sequence.
Which brings us to the fifth difference, planning-aware retrieval. And I think this is the one that really separates RAG inside an agent from agent that has RAG as a tool.
The Archive survey defines planning as a key design pattern in agentic workflows that enables agents to autonomously decompose complex tasks into smaller, manageable subtasks, essential for multi-hop reasoning and iterative problem solving. IBM articulates this through what they call query planning agents. They process complex user queries to break them down into step-by-step processes. They submit the resulting subqueries to the other agents in the RAG system, then combine the responses for a cohesive overall response. The survey gives a concrete example, a query like, what lessons from renewable energy policies in Europe can be applied to developing nations? And what are the potential economic impacts? A chatbot RAG system attempts to retrieve all of this in a single vector search and fails, because no single chunk is going to cover all three components. A planning-aware agent decomposes the query, retrieve European renewable energy policy data, retrieve economic development context for developing nations, retrieve economic impact modeling frameworks, then synthesize across all three.
3 separate retrieval operations, each targeted, each building toward the synthesis. And the synthesis itself might trigger additional retrieval if gaps emerge.
The most sophisticated version of this is what the Archive survey calls adaptive RAG, a classifier that assesses query complexity and determines the retrieval strategy before any retrieval happens. Straightforward queries, no retrieval needed, answer from training data. Simple queries, single-step retrieval. Complex queries, multi-step retrieval with iterative refinement. The system is making a meta decision about how to retrieve before it retrieves anything.
Let's get into the frameworks, because I think the implementation details here are genuinely interesting. LangChain first.
LangChain's key mechanism for intelligent retrieval in agentic contexts is the self-query retriever. Instead of relying solely on semantic similarity, it uses an LLM to parse a user's natural language query and extract structured metadata filters. The Elasticsearch Labs write-up from February 2025 gives a clean example. A user asks, "Find science fiction movies released after 2000 with a rating above 8." A traditional vector search struggles with the date and rating constraints. Those are metadata conditions, not semantic content. The self-query retriever sends the query to an LLM. The LLM identifies the metadata fields, genre equals science fiction, year greater than 2000, rating greater than 8, constructs a structured query combining semantic search with metadata filters, and executes against the vector store. In a chatbot, you might manually engineer these filters. In an agent, the self-query retriever lets the agent dynamically construct precise queries based on whatever context it has at that point in its plan, without the developer having to anticipate every possible filter combination.
The limitation being that it's only as good as the LLM's ability to interpret the query and the quality of your metadata schema.
Exactly those two failure points. If the query is excessively ambiguous or the metadata is poorly defined, you get incorrect or incomplete structured queries, and there's LLM processing overhead on every single query. Then there's LangGraph, which is LangChain's graph-based orchestration layer and the runtime that makes multi-step agentic RAG actually possible. Two features that matter: it supports loops. Unlike DAG-based tools, LangGraph allows cycles, which is what enables self-correction and reflection. And it has persistence. States stored as checkpoints at each super step, enabling fault tolerance and human-in-the-loop approval at defined points. That checkpoint mechanism is what allows you to build the human approves write-back governance model we were talking about earlier.
LlamaIndex's approach is different. They built out a full spectrum from naive to fully agentic, and you can see the progression really clearly.
LlamaIndex's May 2025 blog titled "RAG is Dead, Long Live Agentic Retrieval" lays out 5 levels. Level 1 is naive chunk retrieval, standard top K vector search. Level 2 introduces multiple retrieval modes: chunk mode for standard retrieval, files via metadata for queries mentioning specific file names, files via content for general topic queries that need full file context. Level 3 is auto-routed mode, and this is where it gets genuinely interesting. A lightweight agent determines which of the 3 retrieval modes to use for a given query. You can actually inspect which mode was selected in the metadata after retrieval. Level 4 is composite retrieval. Their Llama Parse Composite Retriever provides a single API to retrieve from multiple indices simultaneously, with an agent layer routing queries to the right sub-index based on natural language descriptions you provide for each index. You describe one index as SEC filings and revenue analysis, and another as slideshows from team meetings, and the agent routes appropriately.
And Level 5 combines both of those into a 2-layer system.
Composite retrieval at the top level, auto-routed mode at the sub-index level. LLM-based classification optimizing every layer of the search path. LlamaIndex's conclusion is direct: naive RAG is dead, agentic retrieval is the future. For these agents to operate effectively and autonomously, they need precise and relevant context at their fingertips. That's the design philosophy driving the whole architecture.
Now, Pinecone, because the infrastructure story here is interesting in a different way.
Pinecone's December 2024 announcement of integrated inference is probably the most significant infrastructure development for agentic RAG in the past year. The old pipeline required managing separate services, an embedding model from OpenAI or Cohere, the Pinecone vector database, and a re-ranking model. 3 vendors, 3 API calls, 3 places for latency to accumulate and things to go wrong. Pinecone's integrated inference collapses embed, store, retrieve, and re-rank into a single unified platform and a single API call. They launched 2 new models with this. Pinecone re-rank for VOR improves search accuracy by up to 60% and on average 9% over industry-leading models on the BEIR benchmark. Pinecone Sparse English v0 is a sparse embedding model for keyword-based queries, up to 44% better NDCG-D10 than BM25 on Trek, 23% better on average.
Why does the single API call matter specifically for agents versus regular RAG?
In an agentic system, retrieval may happen dozens of times per task. Every additional API call adds latency and complexity. If you have a 3-step agentic retrieval loop and each step requires 3 API calls, embed, retrieve, re-rank. That's 9 network hops per loop, potentially 27 total for a complex query. Pinecone's integrated inference gets that down to 3. For an agent that's doing retrieval continuously throughout a long task, that reduction compounds significantly. It also simplifies the agent's tool interface. The agent calls one thing, not 3, which makes the agent's own decision-making cleaner.
Let's talk about the lost in the middle problem, because I know there's a contingent of developers who think the answer to all of this is just bigger context windows.
The argument goes, context windows are now 1 million plus tokens. Just stuff everything in and skip retrieval entirely. Pinecone's 2025 analysis pushes back on this directly. LLMs tend to struggle in distinguishing valuable information when flooded with large amounts of unfiltered information, especially when the information is buried inside the middle portion of the context. This is the lost in the middle phenomenon. It's well documented empirically. Anthropic's research shows prompt caching can reduce latency by 2 times and costs by 90% for repeated context, which is legitimately useful. But you still hit the lost in the middle problem regardless of caching. The information is there. The model just doesn't reliably surface it when it's buried. Retrieval remains the right architecture because it surfaces the relevant information before it goes into the context, rather than hoping the model finds it after.
And honestly, for agentic systems with dynamic knowledge bases, stuffing the whole thing into context isn't even an option. The knowledge base is growing and changing.
You can't snapshot a live knowledge base into a context window. So retrieval isn't just a performance optimization. For agentic systems with write-back, it's architecturally necessary.
Okay, practical architecture. When do you actually use each pattern? Because I think one of the things developers get wrong is reaching for agentic RAG when they don't need it.
ByteByteGo's analysis is refreshingly honest about this. Direct factual lookups against a clean and single-source knowledge base don't need a reasoning loop. Neither do high-volume, low-complexity query patterns where latency and cost matter more than handling edge cases. The cost reality, standard RAG is 1 to 2 seconds, 3 to 10 times baseline cost. Agentic RAG with 3 to 4 loops is 10 seconds or more, 3 to 10 times the cost of standard RAG. If your primary failure mode is retrieval quality, bad chunking, stale data, poor embeddings, fix those before adding an agentic layer. The agentic layer won't paper over fundamentally bad retrieval. It'll just make the failure slower and more expensive.
The practical heuristic being, if most of your failures are in the retrieval step, fix retrieval first. If your failures are in the reasoning about what to retrieve and when, that's where agentic patterns help.
The decision tree roughly looks like this. Simple FAQ chatbot against a stable knowledge base, naive RAG, fast, cheap, predictable. Multi-document research tasks, agentic RAG with multi-step retrieval. Multi-source enterprise data across structured and unstructured sources, routing agent with specialized retrievers per source. Real-time plus historical data combined, hybrid routing between vector database and web search. Continuously improving system where agents should learn, write back, enabled agentic RAG with governance controls. High volume, latency sensitive applications, standard RAG, the agentic overhead is too expensive.
The LangChain survey numbers give some useful context for where the industry actually is. 51% of professionals using agents in production, 78% with active plans to implement. Top use case is research and summarization at 58%, which makes sense. That's exactly the multi-document, complex query scenario where agentic RAG earns its overhead.
And the biggest barrier for smaller companies is performance quality, cited by 45% as the primary concern, which tracks with everything we've been saying. The agentic layer adds complexity, and complexity means more ways for quality to degrade if you haven't nailed the foundations. Cursor, perplexity, replit. Those are the most cited agent applications in the survey. All three of them are doing sophisticated agentic retrieval, multi-source, iterative, planning aware. They're not running naive RAG pipelines.
Before we wrap, I want to come back to the evaluator paradox, because I think it's genuinely the hardest open problem in this space, and it deserves more attention than it usually gets.
It's the Achilles heel of the whole architecture. The self-evaluation loop is what gives agentic RAG its power, the ability to assess retrieval quality and retry. But you're asking the same LLM that might generate a hallucinated answer to judge whether the retrieval that led to that answer was good enough. That's a circular dependency. The practical workarounds exist: separate evaluator model, deterministic signals, but neither fully solves the problem. A smaller evaluator model has its own reliability issues. Deterministic signals like document recency and source authority are useful heuristics, but they don't directly measure whether the retrieved content actually answers the question. This is an area where the research is ahead of the production tooling.
The spectrum framing from the Archive survey is a useful corrective to the binary thinking too. People hear agentic RAG and think it's one thing, fully autonomous, multi-agent, write-back enabled. But the spectrum goes from a simple router that decides between two knowledge bases, all the way up to hierarchical multi-agent systems with graph-enhanced retrieval. Most production systems sit somewhere in the middle, and that's fine.
The simple router is already a meaningful upgrade over naive RAG. You don't have to build the full autonomous system to get value from the agentic pattern. Start with routing, add iterative refinement when you need it, add write-back only when you have the governance controls to support it safely.
Alright, takeaways. What should someone actually walk away and do with this?
3 things. First, audit your current RAG system against the 5 differences we covered. Is retrieval mandatory every turn or conditional? Is query construction naive, raw user message, or agent constructed? Or agent constructed? Do you have a single knowledge source or multiple? Is your knowledge base read-only, or could it benefit from write-back? That audit will tell you where you're leaving value on the table. Second, if you're building new, LlamaIndex's auto-routed mode is a low-friction entry point into agentic retrieval. You get LLM-based routing without rebuilding your whole architecture. And Pinecone's integrated inference meaningfully reduces the operational complexity of adding re-ranking. Third, take the evaluator paradox seriously before you build the self-evaluation loop. Have a plan for what evaluates retrieval quality that isn't the same model doing the generation.
For me, the write-back governance question is the one I'd want anyone building agentic systems to think hard about up front, rather than as an afterthought. Because retrofitting governance controls onto a system that's already writing to its knowledge base is much harder than designing them in from the start. The LangGraph checkpoint mechanism is worth understanding specifically because it gives you the human-in-the-loop hook you need.
And the practical heuristic: if your failures are in retrieval quality, fix retrieval. If your failures are in knowing when and what to retrieve, that's the agentic layer's job.
That's a good place to leave it. Thanks as always to our producer Hilbert Flumingtop for keeping the whole operation running. Big thanks to Modal for the GPU credits that power this show. Genuinely couldn't do it without them. Oh, and today's script was generated by Claude Sonnet 4.6, our friendly AI collaborator. This has been My Weird Prompts. If you're enjoying the show, a quick review on your podcast app goes a long way toward helping new listeners find us. Until next time.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow takes to facts on cue. We change and follow through. My Weird Prompts, that's the close from sloth, from man, from long-eared host. My Weird Prompts, until next time, stay curious, keep weird.